Hello everyone, welcome to Sleepy Sage's Science Diary. Maybe you've had a long day. Maybe you fall asleep while pondering the riddles of the cosmos, rather than counting sheep. Whichever you are, tonight's journey is made for you. Now, please relax, let your thoughts slow down, let your breathing lighten and your body feel weightless, as if even gravity has grown gentle. Next, we'll ask together, why does the universe seem so perfect? And why might time be nothing more than an illusion? By the end of this episode, may you drift to sleep with a calmer, deeper view of the night sky. The distance from Earth to the Sun is about 150 million kilometers. The distance from Earth to the Moon is about 380,000 kilometers. These numbers may seem simple, but in reality, they are essential to the delicate balance that life on Earth depends on. Earth's place in the solar system is no accident. In our solar system, Earth's orbit around the Sun happens to place us in the habitable zone, a very narrow region, with temperate conditions that allow liquid water to exist, and liquid water is fundamental to life. Even tiny shifts in distance could lead to dramatically different outcomes. If Earth were 5% closer to the Sun, temperatures could rise high enough to evaporate the oceans, turning Earth into a scorched and barren desert. Conversely, if Earth were 5% farther from the Sun, our world might become an ice-bound wasteland, where liquid water cannot persist. The Moon's gravity stabilizes Earth's axial tilt, which in turn regulates our climate and seasons. This intricate celestial dance creates an environment where conditions remain stable and predictable, an environment in which life can flourish. If the Moon were significantly farther away, its gravitational influence would weaken, leading to a wobbly axial tilt and chaotic climate shifts. Without that stability, seasons would grow extreme, potentially preventing the steady environments needed for complex evolution. Some 440 million kilometers away from Earth, we find Jupiter. This giant planet acts as Earth's cosmic shield. Its powerful gravity captures or deflects many comets and asteroids that might otherwise strike our world. Without its massive gravitational presence, the inner solar system would suffer heavy bombardment from asteroids, causing frequent and catastrophic impacts, events that could disrupt planetary systems in unpredictable ways, altering their composition and dynamics. As we widen our view further, we see another layer of precision. Our solar system lies in a relatively quiet and stable region of the Milky Way, far from the chaotic and dangerous galactic center, where supernovas and black holes dominate. This location within the Milky Way's galactic habitable zone shields us from excessive cosmic radiation and gravitational disturbances, allowing the solar system to maintain its structure and, on a larger scale, to endure. The universe operates on a set of finely tuned constants and physical laws. Take gravity, for example. If gravity were slightly stronger, stars would burn through their fuel more quickly, possibly before planetary systems could even form. Rapid collapse of matter would produce a cosmos dominated by black holes and neutron stars, leaving little room for the diverse structures we observe today. If gravity were weaker, matter would struggle to clump together, hindering the formation of stars and galaxies. The masses of subatomic particles, such as protons and neutrons, are finely set as well. If the proton's mass were even slightly different, the balance of protons and neutrons in atomic nuclei would break, undermining atomic stability. If protons were significantly heavier, they might decay more readily, reducing the stability of matter. If neutrons were lighter, nuclei could not bind stably, blocking the formation of elements essential to stellar and planetary evolution. All the constants and laws in our cosmos are set at values that permit galaxies, stars, and planetary systems to form. Tiny changes to any of these numbers could yield a profoundly different universe. One with no galaxies, no stars, no planets, and perhaps no complex structures at all. A universe lacking the delicate balance required for life. A universe without us. So, how does such a delicate balance exist? Where do the precise configurations that govern the solar system, the Milky Way, and the entire universe come from? Are these perfect conditions a random coincidence, an inherent necessity, or the result of some underlying design? Is such fine-tuning merely chance, or does it hint at a deeper, more profound order to the cosmos? 13.8 billion years ago, the universe began from an extremely tiny point. It was so small that to measure it, you'd need a ruler so precise it could count the hairs on a bacterium's back. Imagine holding a speck of dust on your fingertip, then shrinking it to 1/10,000th of its size. Still nowhere near the scale of the beginning. Yet in that minuscule point was all the energy and matter of the cosmos, the seeds of every galaxy, star, planet, and of life itself. The starting point was not only unimaginably small, but also unimaginably hot and dense. Its temperature soared into the trillions of degrees, so extreme that atoms could not exist, and even protons and neutrons melted into a scorching dense soup of fundamental particles and energy. If you could somehow withstand the heat and look at that beginning, you would see no solid matter, no familiar scenery, but a blazing, boiling cauldron filled with primordial energy and particles. In terms of density, this beginning defied every concept we know. The density was so great that even the fabric of space-time warped, curved toward infinity. Matter and energy were compressed to such extremes that our current physical laws cannot fully describe the conditions. This tiny, fiery, ultra-dense point marked the origin of everything. It posed a paradox, so insignificant in size, yet harboring infinite potential. At that almost inconceivably small point, everything seemed to wait for a beginning. But the starting state was profoundly unstable. Its colossal energy density and extreme temperature could not be maintained for long. Eventually, this instability triggered a sudden transformation, the expansion we now call the Big Bang. Contrary to its name, the Big Bang was not an explosion in space. It was the expansion of space itself. From this moment, space rapidly stretched, and time began to flow. It was an extraordinarily rapid expansion. Space itself was pulled and extended, with primordial particles and energy moving within it. But the Big Bang was only the opening chapter. Shortly after the Big Bang, the universe entered a special accelerated phase of expansion called inflation. This phase was extremely brief, yet it had profound consequences. Think of inflating a balloon. Tiny bumps and imperfections on the surface. It gets smoothed out as it expands. Likewise, any initial clumps or irregularities in the early universe were stretched apart, leading to the smooth, uniform cosmos we observe today. This smoothing was no accident. It was a precise, delicate process. Consider the universe's expansion rate during inflation. If it had deviated even slightly, the consequences would have been catastrophic. If, 1 second after the Big Bang, the rate were a little lower, the universe would have collapsed back on itself before it had a chance to expand. If slightly higher, matter would have thinned out too quickly, preventing the formation of galaxies, stars, and planets. As expansion continued, the four fundamental forces separated: gravity, electromagnetism, the strong nuclear force and the weak nuclear force. Their strengths had to be exquisitely precise for the universe to unfold as it did. If the strong force were slightly weaker, atomic nuclei could not hold together. The atoms we know would not exist. If slightly stronger, stars would burn too rapidly, undercutting the long-term stability needed for life to evolve. In the early universe, fundamental particles like quarks and electrons formed, combined into protons and neutrons, and then fused into the first atomic nuclei, a process called nucleosynthesis. During this brief window, the neutron-to-proton ratio was critical. A significant imbalance would have left a cosmos of mostly hydrogen and helium, blocking the later formation of heavier elements necessary for life. Though nucleosynthesis lasted only minutes, it laid the chemical groundwork for everything to come. As the universe expanded further, it reached a pivotal moment called recombination. Protons and electrons paired to form neutral hydrogen atoms. This allowed photons to travel freely, releasing the cosmic microwave background radiation we can still observe today. During this stage, the universe also cooled, and the cooling rate was crucial. Too fast or too slow, and the formation of atoms and later structures would have been disrupted. Continuing to expand and cool, the universe reached another key moment. Electrons could bind with nuclei to form neutral atoms. About 380,000 years after the Big Bang, the timing of recombination mattered. Too early or too late, and the distribution of matter and radiation would have been very different. Before recombination, the universe was opaque. Free electrons scattered photons, preventing them from traveling far. After recombination, photons moved unimpeded, producing the cosmic microwave background. The CMB gives us a snapshot of the infant universe, showing tiny temperature fluctuations, seeds of future galaxies. Its uniformity, along with those minute variations, attests to the fine balance achieved at recombination. Then came the so-called Dark Ages, lasting roughly from 150 million to a billion years. No stars or galaxies shone. Neutral hydrogen-filled space, cooling rates, initial density ripples, and remnants of inflation's imprint eventually aligned, allowing gravity to amplify those ripples, drawing matter together, and the first stars and galaxies were born. If the density fluctuations had been larger or smaller, cosmic structure would be utterly different. As gravity amplified small overdensities, the earliest stars and galaxies emerged, ushering in the epoch of reionization. Ultraviolet light from the first stars ionized surrounding hydrogen, making the universe transparent to UV light. The timing and intensity of reionization were critical for shaping the large-scale structure of the cosmos. Dark matter, a mysterious substance that neither emits nor absorbs light, played a major role. Though invisible, its gravity provided the scaffolding on which visible matter could collect. Without dark matter, galaxies and larger structures might not have formed as we see them. The precise distribution and amount of dark matter were crucial to cosmic evolution. Dark energy, another enigma, began to influence expansion more strongly in the recent universe. It acts as a driver of accelerated expansion. Over time, its influence has grown, shaping the expansion rate of the cosmos. The balance between dark matter and dark energy is yet another fine-tuning. If dark energy were stronger or weaker, it could have stifled galaxy formation or sped expansion so much that structures never coalesced. The birth of the first stars marked the dawn of cosmic day. Matter condensed under gravity and stars ignited. Gravity's strength was just right. Had it been weaker, matter could not clump and stars would not light. stronger, and the universe might have collapsed. Before stars formed, these first-generation stars lived full lives, many ending as supernovas, spewing heavier elements across the cosmos. Those elements were essential for planets, and, ultimately, for life. Stars, pulled together by gravity, slowly assembled into galaxies. Galaxy formation required a delicate balance between gravity and the rate of cosmic expansion. Hubble's law describes the recession speed between galaxies and is key to that balance. The Hubble constant measuring the expansion rate is another example of fine-tuning. If the rate were different, galaxies might not have formed, or expansion might have run so fast that life never had a chance. Galaxy clusters, vast groupings of galaxies, formed under specific conditions: cooling of the universe, density fluctuations, and the influence of dark matter, all contributed. A precise balance of gravity and expansion was necessary to build these clusters. Our Milky Way, and the local group it inhabits, are products of this fine-tuned process. The Milky Way's formation was complex, shaped by collapsing gas clouds, rotation, and dark matter. These factors endowed it with a spiral structure and habitable zones, conditions favorable to life-bearing worlds. The Milky Way's features stand as a vivid example of cosmic fine-tuning. Within the Milky Way, the solar system's formation depended on highly specific conditions: a protoplanetary disk, heavy elements forged in ancient supernovas, and the sun's stability. Together, these produced our planetary family. The sun's steady energy output, the solar system's location in the galaxy, and the unique triggers of planet formation highlight the precise tuning required for our existence. Earth's formation relied on multiple finely balanced factors: accretion of planetary material, the presence of water, the moon's role in stabilizing Earth's tilt, and a seat in the habitable zone. The right distance from the sunday. Earth's magnetic field shields us from solar radiation, and Jupiter plays a crucial part in deflecting impact threats. A life-friendly atmosphere completes this suite of conditions. Together, they make Earth a habitable world. Life on Earth depended on precise conditions: liquid water, the right chemical elements, and a stable climate. From the rise of complex organic molecules to the first stirrings of life, and then to ecosystems evolving, everything required a finely tuned environment. From single-celled organisms to complex multicellular life, evolution through mutation and natural selection needed stable niches and long timescales to unfold. Why do stars burn at just the right pace? Why do atoms form as they do? Why didn't the universe collapse on itself? Shortly after the Big Bang, these questions lead to the intriguing idea of cosmic fine-tuning, that the universe's basic constants and quantities are set with exquisite precision, allowing life to exist. Think of tuning an old radio. You have to adjust the dial to just the right frequency to get a clear signal. Drift a bit, and you hear only static. Likewise, if the universe's fundamental parameters were slightly different, life as we know it could not exist, and the universe's evolution might have taken a wholly different path. This concept took shape in the mid-20th century, thanks in part to the pioneering work of physicist Fred Hoyle in the 1950 seconds, studying how carbon vital to life is forged in stars. Hoyle discovered that carbon production depends on a highly precise resonance level in the carbon nucleus. If that resonance were shifted even slightly, carbon could not form, and life would not exist. Hoyle famously remarked that the universe looks like a put-up job, suggesting that its structure and constants seem tailored for life. Since Hoyle's time, scientists have found many more examples. The strengths of the four fundamental forces, gravity, electromagnetism, the strong force, and the weak force, are delicately balanced. Slightly stronger gravity, and stars burn too fast to sustain life. Slightly weaker, and stars might never ignite. Electromagnetism must also be just right. It governs the chemistry of atoms and molecules. Shift it, and atoms couldn't bind properly, making complex, life-bearing molecules impossible. Fine-tuning also reaches back to the universe's initial conditions. The Big Bang, the event that brought the universe into being, had to be extraordinarily precise. For instance, the initial density needed to be balanced to within about 1 part in 10 circumflex 60. Picture a ruler spanning the observable universe, marked in inch-long increments. The initial density had to be tuned within a tiny sliver on that vast scale. Otherwise, the universe would have collapsed under its own weight, or expanded too fast for galaxies, stars, and planets to form. The cosmological constant is among the most striking examples. It drives the universe's accelerated expansion. Its value is incredibly small, but not zero. If it were much larger, expansion would outrun structure formation. If negative, the universe would collapse. Astonishingly, the cosmological constant appears tuned to about 1 part in 10 circumflex 120, a level of precision that boggles the mind. Why should the universe be arranged so precisely to support life? One proposed answer is the anthropic principle. We observe a finely tuned cosmos because, without such conditions, we wouldn't be here to observe it. In other words, the universe must have properties compatible with observers, because our very existence depends on those properties. In the 1960 seconds, physicist Robert Dicke helped develop this line of thought, and in 1973, Brandon Carter formalized it at a conference marking Copernicus's 500th birthday, distinguishing a weak anthropic principle, WAP, from a strong anthropic principle, SAP. The weak version says, we should recognize that our place in the universe is necessarily privileged, at least to the extent required for observers to exist. The laws and constants look tuned for life, because if they weren't, we wouldn't be here to notice. This is largely an observational statement, without implying anything beyond the fact that the universe allows observers. The strong version goes further. It suggests the universe must have properties that inevitably lead to intelligent life. Some interpretations even hint that the universe is, in some sense, shaped or driven to produce life and observers. Think of the weak principle like a cosmic lottery. Holding a winning ticket means that, among countless outcomes, you experienced the one that allowed you to win. Likewise, among all possible cosmic configurations, we find ourselves in one that supports life. Only such a universe contains observers like us. The anthropic principle has sparked lively debate among scientists and philosophers. Critics argue that it isn't a true explanation, merely a restatement. We observe a life-friendly universe because we live in one. Supporters counter that it's a useful framework and fits naturally with multiverse ideas, where many universes may exist with different constants and laws, most inhospitable to life, and we happen to be in one of the rare, life-permitting cases. The multiverse has roots in several sources. One early form comes from the many worlds interpretation of quantum mechanics, proposed by Hugh Everett in 1957. The idea that all possible outcomes of quantum events occur in separate branch universes. In cosmology, the concept gained momentum in the 1980 seconds, with inflationary theory from Alan Guth, Andre Linde, and others. Inflation may produce causally disconnected bubble universes, each with its own properties. Linde, a strong multiverse advocate, proposed eternal inflation. It could spawn an unlimited number of such bubbles. Proponents argue, the multiverse elegantly addresses fine-tuning. If countless universes exist with varied constants and laws, then it's unsurprising that at least one supports life, and we live in it. The question shifts from why is our universe so tuned to how many universes are there? Critics reply that the multiverse may be untestable by definition. Other universes are causally disconnected, beyond observation or interaction. Without empirical tests, the idea risks drifting from science into philosophy. Still, it offers deep insights and dovetails with cutting-edge theories like string theory, where the basic constituents are tiny vibrating strings, and extra dimensions can be compactified in myriad ways, yielding different physical laws and constants. A vast landscape of possible universes. Even so, string theory faces major challenges: a lack of direct experimental confirmation, mathematical complexity that hampers clear predictions, and the sheer size of the landscape, which complicates testability. Another provocative idea is the simulation hypothesis. Philosopher Nick Bostrom popularized it in 2003 with a trilemma. At least one must be true. 1. Civilizations like ours go extinct before they can run ancestor-like simulations. 2. They can but choose not to. 3. We are likely living in a simulation. If a highly advanced civilization had colossal computational power, it might simulate conscious beings who would not realize they were simulated. Supporters point to accelerating tech, AI, VR, and perhaps quantum computing. Skeptics note the lack of empirical evidence and the problem of infinite regress. If we are simulated, what about the simulators? The fine-tuning often cited for intelligent design meets a sobering paradox. A universe with precise constants also teems with chaos and catastrophe. Black holes, gamma-ray bursts, supernovas, and vast, lifeless expanses dominated by dark matter and dark energy. If designed, why the overwhelming hostility to life? Perhaps imperfections are not flaws but engines of change, seeding evolution and complexity. Dark matter and dark energy together make up roughly 95% of the cosmos. About 27% dark matter, 68% dark energy. Dark matter clusters into gravitational wells, scaffolding galaxies and clusters, yet its true nature remains elusive, despite intense searches. Dark energy, likely a property of space itself, drives accelerated expansion, its distribution and essence, to remain among cosmology's greatest mysteries. These imperfections and unknowns shape the universe's evolution and fate. Baryon asymmetry, the imbalance of matter over antimatter, adds to the puzzle. The Big Bang should have produced equal amounts, yet we observe a matter-dominated universe. This asymmetry is crucial to our existence and remains unsolved. Ironically, imperfections are what made structure possible. In a perfectly uniform cosmos, gravity would have nothing to pull on, no overdensities to amplify, and no stars or galaxies would form. Tiny quantum fluctuations in spacetime seeded slight density variations, which gravity magnified over millions and billions of years, into the grand structures we see today. Supernova shocks compress gas and dust, igniting new generations of stars. Heavy elements forged in dying stars become the building blocks of planets and life. Without asymmetry and messiness, the universe would be a smooth, lifeless soup. These themes echo in biology. Mutation errors in replication is the raw material of evolution. Under selective pressure, some variations confer advantage, like antibiotic resistance in bacteria, and spread. Dynamic environments carve diverse habitats, from deserts to rainforests, driving adaptation and resilience. Life on Earth has repeatedly endured upheavals, ice ages, asteroid impacts, evolving and flourishing in their wake. Recognizing imperfection also humbles our perspective. Our cosmology is limited by human frames of reference. Different cultures and philosophies offer distinct readings of the cosmos. Welcoming that plurality broadens inquiry and deepens understanding. In the vastness of space, life's fragility and rarity heighten its value. Protecting Earth's ecosystems, addressing climate change, habitat loss, pollution, is an ethical imperative. As we explore space, we should do so with respect and responsibility, mindful of possible extraterrestrial ecologies. We are stewards of Earth, and perhaps, one day, of other worlds. The universe's imperfections are not defects, but sources of vitality and change. They challenge us to appreciate complexity and beauty, to keep seeking deeper understanding, and to carry ethical responsibility. It is these irregular threads that weave the cosmos's evolving tapestry, prompting us to reflect on our place and our duties as inhabitants of this extraordinary realm. In exploring the universe, we find astonishing fine-tuning in physical constants. Stars can burn, planets can harbor life, and complex beings can contemplate their own existence. It's tempting to imagine a hidden blueprint or guiding hand, yet behind this near perfection lie profound irregularities, from galactic collisions to quantum fluctuations, reminding us that the universe is not static, but in ceaseless flux, full of surprises. Looking ahead, our dual grasp of fine-tuning and imperfection will matter greatly. Science pushes the frontier. Physics, cosmology, origins. Each insight brings new questions, calling us further into the unknown. Wonder should be paired with ethics. Our future understanding depends on a delicate balance, the marvel of fine-tuning and the riddle of imperfection, with curiosity, rigor, and moral awareness. As we press the frontiers of knowledge, we deepen our sense of the universe and of ourselves within it. Humanity often assumes it is unique, placing itself at the center of theory, measuring all by human scales. But not all structures must be human-centric. We compress reality into models we can grasp, and in doing so, risk ignoring its vastness and unimaginable complexity. If the universe is not wholly governed by our mathematics, and humans are not the sole measure, what then legitimizes existence? The only true measure is time. It witnesses that things are. Without the flow of time, our existence loses meaning. Imagine a river, gliding with a steady rhythm. Water slips past rocks, spiraling into eddies. From afar, the river looks like an unbroken ribbon from peak to valley. Stand by its bank long enough, and you notice it is never the same twice. The water you see now is not the water you saw before. Heraclitus said, "You cannot step into the same river twice. Each drop that passes is gone forever, replaced by new currents rolling onward." We often picture time as a similar current, carrying us from past to future, on a tide that never stops. Every moment is new, arriving quickly, leaving quickly, and like a river bending or slowing, time can stretch or compress. Einstein showed that time can be stretched or squeezed, depending on where you are and how fast you move. Race along the river at extreme speed, and the banks blur, while to someone seated on the shore, the water seems slower, almost still. So too with time. Move near light speed, and time runs slower for you than for someone at rest. Imagine a river that freezes when it stops. Water is trapped in a single moment, crystallized in sunlight. Under extreme conditions, time itself can seem to pause, as if the surface has turned to glass. The flow halted below, near black holes, where intense gravity warps space-time. Time slows to a crawl, almost to a stop. We assume time always moves forward, but in such extremes, the river of time grows sluggish, nearly frozen, bound by gravity's grip. We live inside this flow and feel time rushing by. But look closely, and it's not so simple. If rivers can bend, halt, or stretch, why not time? Is time truly relentless? Or is it an illusion? Time's arrow points one way, from past to future. Waves crash and recede. Leaves fall and decay. Energy dissipates in irreversible processes. Why this one-way flow? Is it fundamental to the universe, or a quirk of human perception? The answer may hide in small details, deep within reality's fabric. In the age of steam, engines drove trains across continents, powered factories, and reshaped society. Yet a puzzle lingered. Why did these machines waste so much energy? And why could none run forever? Rudolf Clausius grappled with this. Heat, he realized, was not a mysterious caloric fluid, but energy in transfer. Watching engines pour heat into the air, he asked, why does energy flow one way, from hot boilers to cold air, from ordered motion to disorderly heat? After years of experiments and calculations, he distilled a revolutionary insight. The second law of thermodynamics. In any closed system, entropy never decreases. Energy disperses. Order decays. Some transformations are irreversible. This invisible slide toward disorder sets limits on engine efficiency and reveals a fundamental law of the universe. Picture an engine with two chambers, one filled with hot steam, the other cooler. Steam rushes from hot to cold, pushing a piston, turning a wheel, converting some heat into work. But not all heat becomes useful work. Some always leaks away as waste, warming the environment. No design can prevent this loss. Heat flows from hot to cold, never the reverse. Clausius saw that this one-way flow is the heart of the second law. Entropy rises. Hot things cool. Order tends toward disorder. Once entropy increases, reversing the process is effectively impossible. Think of a box with 100 marbles. At first, all red on one side, all blue on the other. A low entropy, highly ordered state. Shake the box. The marbles mix. After a while, color is scattered everywhere. A high entropy state. Spontaneously unmixed marbles? Astronomically unlikely. That's entropy. Once disorder rises, it almost never reverses on its own. Entropy also gives time its direction. We remember the past, a low entropy arrangement, but not the future, the realm where entropy is higher. Your morning coffee cools. Steam drifts away. The heat spreads into the room. Entropy rises. You never see steam gather itself and warm the coffee again, unless you add energy, a microwave, which increases entropy elsewhere. Crack an egg. A neat, low-entropy system becomes mixed. Cooking disperses energy and alters structure. To restore the pristine egg would require manipulating every molecule with absurd precision, practically impossible. From match to ash, from whole egg to breakfast, entropy's rise makes time's arrow point forward. Modern life depends on precise timekeeping, and relativity makes it tricky. GPS works only because we correct. for both special and general relativistic effects. Satellites, moving fast and high above Earth's gravity, tick at different rates than clocks on the ground. Without corrections, GPS would drift by kilometers per day. Even keeping civil time aligned with Earth's rotation requires leap seconds. When that extra second is added, computer systems can stumble, because many weren't built for a duplicated or missing second. To soften the impact, engineers sometimes smear the leap second by stretching each second slightly over 24 hours. A clever hack to dodge sudden glitches. And what if we could not just smear seconds, but freeze them? Quantum theory teases us with possibilities that stretch the borders of time itself. In 1963, a young Kip Thorne stood in John Wheeler's office, captivated. Wheeler spoke of massive stars collapsing into points of infinite density, black holes, where gravity overwhelms all else, and space-time is grotesquely curved. Thorne would spend a lifetime probing how extreme gravity shapes time. Near a black hole's event horizon, time dilates intensely. From far away, objects falling toward the horizon seem to slow. Their light redshifts until they fade from view, as if frozen at the brink. From the falling object's perspective, however, time feels normal. It crosses the horizon without noticing a boundary. Closer to the singularity, space-time curvature grows without limit, and our theories fail, calling for quantum gravity to take over. What happens to information that falls in? Does it vanish, violating quantum principles? Or is it somehow preserved? Gerard 't Hooft and Leonard Susskind forged the holographic principle. Information about a volume of space can be encoded on its boundary, as with a black hole's horizon. Perhaps our entire universe is a kind of hologram, the three-dimensional world we experience, emerging from more fundamental data, written on a distant two-dimensional surface. This idea resonates with the block universe. Past, present, and future coexist as coordinates in space-time. Carlo Rovelli's relational view of time suggests the present has no absolute meaning. What we call time may be bookkeeping for change. Julian Barber pushes further. Reality is a vast configuration space. Platonia, a collection of timeless nows. Our sense of flow arises from how records and memories are arranged within certain regions of this space. Subjectively, time is elastic. In flow, hours vanish. In fear, seconds stretch. The brain stitches asynchronous signals into a coherent now, introducing delays and illusions, from time binding to motion prediction, reminding us that the present we feel is a best guess, not a raw feed of reality. So what is time? If clocks and calendars are tools, not essences, if our awareness lags behind events, if physics sometimes treats time as a dimension, and sometimes as an emergent pattern, then perhaps the wisest course, for now, is to hold the question open and cherish the time we have. Whether time is fundamental or illusory, it is central to human experience. By focusing on the present, shaping our relationships and actions, and tending what we can actually influence, we can strive for a life well lived. No matter what time truly is,